Hi, welcome to TemurTube. In the last video, we used the Kiwi3D Grasshopper plugin to analyze a warrant trust system. We successfully ran the model, observed the internal forces, and checked how much each section was utilized. In today's video, we'll explore how to optimize our truss using optimization solvers. Our goal is to minimize the total volume of the truss while ensuring that the maximum utilization factor remains equal to 1. First, let's extract the maximum value of the utilization factors. Since our list is sorted from minimum to maximum, we need to extract the last item. We'll use the list length component and subtract 1 to get the index of the last item. Then, using the list item component, we'll retrieve the last value, the maximum utilization factor for all truss members. Because we want this value to be close to 1, we'll subtract the maximum value from 1 and feed it into our minimization function. Since the minimization process tries to make this difference 0, we can ensure that the maximum utilization remains near 1. We'll also take the absolute value of this number in case it goes below 0. Next, let's determine the total volume of our truss members. We'll start by calculating the total length of the diagonal members using the curve length component, followed by mass addition to get the total length. Since our diagonals are circular, we can use the circle and area components to find a cross-sectional area. The radius is obtained by dividing the diameter input by 2. Once we have the area, we'll multiply it by the total length to find the volume of the diagonal members. We'll repeat the same process for the top and bottom chord members. For these, the area is obtained by multiplying the length and width of the cross-section. Let's move the components to the right for better organization. To perform our optimization, we'll use the Opossum plugin. You can install it and request a free license via email. Opossum is a multi-objective optimization plugin, meaning we can minimize or maximize more than one objective simultaneously. In the objective input, we'll connect the total volume and the maximum utilization factor. Next, let's adjust our variables. Our variables are the member dimensions which will change during the optimization process. We'll allow the members to vary between 0.2 meters and 0.7 meters. Since the size of the utilization factor has less influence compared to volume, and we want to enforce that it stays near 1, we'll assign a higher weighting factor to it. We'll multiply the utilization factor by 1,000 before feeding it into the solver. Now, instead of connecting the raw utilization factor, we'll connect this amplified value. Let's use recorders to track changes in the member dimensions during optimization. We'll use 3 recorders, one for each variable. Now, let's run the optimization solver. You'll notice several algorithms available. We'll use the default one. We'll reduce the number of iterations to 25. Before starting, toggle the Run button of the Kiwi3D solver to True. Let's also display the utilization factor in a panel to observe changes. Now, run the solver. The total iteration takes a few minutes, and you'll see the Kiwi3D solver window during every iteration. Once optimization is complete, check the Results section. Select the best result. the one with the least volume and a utilization factor close to 1. Save and close it. As you can see, the maximum utilization factor is 0.2, which is well below 1, and the volume is about 2.5 meter cubes. Let's review the selected dimensions after optimization. The optimizer reached the smallest dimensions, which prevented it from reaching a utilization factor of 1. Let's reduce the minimum dimension to 0.1 m and run the solver again. Now, the utilization factor has increased to 0.83, and the volume has decreased to 0.62 meter cubes, an improvement from before. When we check the dimensions, the solver again used the smallest values for all variables. Let's increase the nodal loads to 100 kilonewtons and run the solver again. For the increased load, the utilization factor is above 1, and the volume is approximately 1.4 meter cubes. We need to increase the weight of the utilization factor to bring it back to 1. Let's raise the weight to 10,000 and run the solver again. As you can see, the utilization factor is now almost 1, and the volume has increased to about 2 meter cubes. The sections are more evenly loaded. If we had used different sections for each member, we might have achieved an even more optimal volume. We can view the history of changes in member dimensions from our recorded data. Thanks for watching. I hope this video gave you some insights into optimizing structural systems. If you found the content useful, don't forget to like and subscribe. It helps us create more content like this.